morning everybody. Hope you're all healthy and safe at home. Now we are moving on to the next session of this module, that is section 9.12, and this section mainly deals with a theorem which is called as the Green's theorem. We are just going to discuss about the Green's theorem and do a few problems related to it in this section. So before knowing what is meant by Green's theorem, we should understand the concept of the positive direction that we are going to choose. So we know that we have learned about simple closed curves in previous sections and all. So here let me just read out what is the meaning of positive direction of a curve. Now the positive direction around a simple closed curve is that direction a point on the curve must move, or the direction a person must walk on the curve C in order to keep the region R bounded by C to the left. Is it clear? What is meant by positive direction? Suppose can you see this figure? Just consider this figure and this region. Okay, then the positive direction of this curve will be along the direction or along the path in which we are moving. Let me just consider a point over here. When I move this point like this, okay, then it's better you imagine yourself. Just imagine you're standing here and you're walking in this direction. Then on which side will the region lie? The region will lie on the left side, on your left side. Okay, if I'm standing here and if you're moving in this direction, then the region will be on your right. So that is not the positive direction. Here the positive direction is that direction in which when you move along that curve, just imagine yourself moving along the given curve, then the region should lie on your left. Okay, suppose if you consider the R to be here, okay, outside this curve, then what will be the positive direction? It will be straight opposite, right? If I'm walking in this direction, then the curve will be on my left. So just imagine when you're given a curve, imagine yourself standing on that curve and moving along that curve, and the positive direction is that direction in which the region will lie on your left. Okay, that is the meaning of positive direction, and the negative direction will be the other way around. And generally we consider, see, you can see the second point here, that is we can see the counterclockwise and clockwise direction. Usually the counterclockwise direction will be the positive one and the clockwise direction will be the negative one. If you see, I'm just going back to the previous slide, you can see the figure here. The counterclockwise, this direction is the counterclockwise direction, right? So counterclockwise direction is treated to be the positive direction and the clockwise direction is treated to be the negative direction. Now the line integrals on a simple closed curves are generally written as integral, and you can see, you know how we know that how a line integral is written. This is integral p of x comma y dx plus q of x comma y dy. The only thing that is new here is there is a circle over this integration sign. Okay, this denotes the concept of a closed curve, simple closed curve. Okay, so the line integrals on a simple closed curves are written in this form. Okay, so in this section we'll be dealing with line integrals on a simple closed curve. Now there is one more thing that you should note, that an arrow in the counterclockwise direction will show that the region is in the it depicts the direction. Okay, on this circle it depicts the direction, whether it is positive or correspondingly if it is clockwise the direction will be negative. If it is clockwise the direction is negative, and if it is anti-clockwise the direction is positive. The corresponding arrows will give us the sense of the direction also. Now keeping all these things in mind, we shall move on to Green's theorem in a plane. let's see what the theorem states. The theorem states that suppose that C is a piecewise smooth simple closed curve bounding a simply connected region R. The one that you have seen in the first slide depicts the same thing, so the terminologies don't get confused. It is just we are given a region which is bounded by a simple closed curve, okay, and it is a connected region. Now if P, Q, do P by do Y and do Q by do X are continuous on R, remember they have to be continuous on R, then the integral over simple closed curve P dx plus Q dy can be easily written as double integral over the region do Q by do X minus do P by do Y into dA. Okay, so to evaluate the line integral on a simple closed curve, it is enough to evaluate the double integral over the region, which we have been doing in the previous section and all. So let us now see how we can prove this part of the theorem. So we will be dealing with only the partial proof, that is we'll consider only the type of region of type 1 and type 2. Okay, that is we are just going to deal with the regions. If you remember, we had considered two regions of type 1 and regions of type 2. So this is not the complete proof of Green's theorem, because we are just going to consider the region which is both simultaneously of type 1 and type 2. So I'm just drawing a figure here. Okay, they should be actually similar, somewhat kind of similar. So this region R can be considered to be the one, this is my x-axis and y-axis, can be considered to be both of type 1 and type 2, right? If I am marking this particular point over here, this is my A and this is my B, and if I consider along y-axis, this is my C and this is my D. Okay, all right, and now I'm going to plot the arrows. Okay, from A to B I'm moving in the counterclockwise direction. Okay, and here also from C to D I'm moving in the counterclockwise direction. So here we have y is equal to g1 of x, and in this portion y is equal to g2 of x, and similarly in this portion we have x is equal to h2 of y, and oh sorry, this is h2 of y, and here we have x is equal to h1 of y. So we are going to prove this Green's theorem for only those regions. So this is a partial proof, not a complete proof, as I mentioned before, only for those regions which are both type 1 and type 2. Okay, this is our type 1, that is we are having constant values for x, and type 2 will be the constant value for y. Okay, so we are going to consider only those regions which are both simultaneously type 1 and type 2, and we are going to give the proof of Green's theorem for this type of region. So let me just begin with the proof. Let us evaluate what will be minus double integral over R dou P by dou Y into dA. Okay, this will be nothing but I am just substituting the values, that is integral A to B. This is I am considering the first one, that is type 1. Okay, that is x is having a constant limit, so integral A to B, and integral g1 of x to g2 of x dou P by dou Y dy into dx. dA will become dy into dx. Now let me just integrate the first part. Now integration and differentiation, these both will get cancelled out and we will get the function p, right? Integral of dou P by dou Y is nothing, with respect to y is nothing but p itself. So this will be integral A to B p of x comma, we'll apply the limits also simultaneously. So first one will be g2 of x, right? Let me use a square bracket here, minus p of x comma g1 of x into dx. Okay, so this is what will be the integral of dou p by dou y with respect to y. We will get p of x comma y, and we have to substitute the value of y varying from g1 of x to g2 of x. So we'll get this value. Now let me take this minus sign inside. So I will get integral a to b p of x comma g1 of x minus so that will be plus integral of a to b p of x comma g2 of x. So from this, if you remember the figure, if we move from integral a to b, okay, wait a minute, there is a minus sign over here, right? This is minus. So we have integral a to b p of x comma g1 of x minus integral a to b p of x comma g2 of x. Now if I change this limit, the minus sign, negative sign will become positive. So this will become nothing but integral a to b p of x comma g1 of x plus integral b to a p of x comma g2 of x. Now if you see the figure, you can see that in type 1 region, when we move from a to b, it is we have moved from a to b, we'll get 1p, right? And then we'll moving from b to a, we had changed the limit. So altogether, after the complete rotation, that is from a to b and b to a, we will get the area of this whole thing. So that is what we have done over here, that is integral a to b p of x comma g1 of x plus integral b to a p of x comma g2 of x. So finally, adding these things, we will get the required integral. So that is nothing but integral over c in the counterclockwise direction p of x y dx. I hope it is clear. First we consider the region of type 1, and we had evaluated the value of double integral over r dou p by dou y, that is same as the line integral over c p of x comma y dx. Now similarly, we can calculate double integral over r dou q by dou x into dA. Okay, in this case we will consider the region of type 2. So this will be here y will be having the constant limits, so integral varying from c to d and integral varying from h1 of y to h2 of y into dou q by dou x dx dy. So again, when we integrate dou q by dou x partially, when we integrate dou q by dou x with respect to the x itself, we will get it to be q of, instead of x we have to apply the limiting value, so it will be q of h2 of y comma y minus q of h1 of y comma y into dy, right? So here again, like the previous case, what we are going to do, we will complete, or we'll change the limits, and we get integral over integral from c to d q of h2 of y comma y plus integral, it is actually minus integral c to d, so it will be d to c. Okay, q of h1 of y comma y into dy. So again, if you recall the figure that we have seen, type 2, here from d to c we have x is equal to h1 of y, so from d to c we are moving, then from c to d again. So when we cover this whole integral, we'll get the circle, we'll cover this whole region along the curve c, and the integral will be correspondingly the line integral over the closed surface. So this value will be nothing but equal to, that is equal to integral, you see, q of x comma y dy. Okay, so what I'll just write what we had obtained. We had obtained minus of double integral over r dou p by dou y into dA is equal to the line integral over the closed surface p of x comma y dx and double integral over r dou q by dou x into dA is equal to line integral over closed curve c into q of x comma y dy. So if I add these two equations, what do I get? Line integral over the closed curve p of xy dx plus q of xy dy is equal to, what is it? Minus double integral over r dou p by dou y plus dou q by, oh sorry, the negative sign is inside not outside, dou q by dou x into dA. Or I can also write this as, how can I write it? I can write integral over c p dx plus q dy is equal to double integral over r, I'm just interchanging the negative sign, dou q by dou x minus dou p by dou y into dA. Okay, so I hope the proof is clear for you all. So just as I had mentioned in the beginning of this proof, that this is just a partial proof because we were just considering the region which were both simultaneously of type 1 and type 2. So this is the Green's theorem, that is the integral over a simple closed curve can be evaluated by using the double integral. And the one thing that we must keep in mind is that the functions p, q, dou p by dou y and dou q by dou x must all be continuous. So with this we shall wind up today's session. Thank you. Stay home and stay safe.